Welcome aboard, my dear lovely NEET warriors, to the Vedantu NEET English channel. And this is your Captain Shreyas, your physics master teacher who has been training kids for more than 13 plus years. So today we put an end to electrostatics and Gauss law, the final nail, which is the flux concept, the Gauss law concept, and how we apply Gauss law in different scenarios where you find the electric field due to different geometry. So the application part as well. Now Gauss law and its applications along with flux is a very important aspect of electrostatics and of course capacitors, and even in the future you will see in magnetism we will talk about flux. So today we are going to do that. Hi Fahira, welcome everyone out there on the Vedantu NEET English channel. I know this lecture was long due, so I hope you have first of all liked this video and subscribed to the Vedantu NEET English channel. So as you are watching this particular video, remember that yes, you have to first of all subscribe so that you get all the daily updates and everything. See, after the video ends, in the description box and everything, I'll be putting up the notes and all of that. And of course, in the comment section also, you will find the PDF of whatever notes we are, writing over here. Okay. And for all the students who still want the entire syllabus to be covered in a very systematic manner with test series and, the Tattva books, the soft material, the test series for all India level, along with DPPs and a guided mentorship. The DNA batch is still live, so make sure you check it out. The link is there in the description box. Yeah, all the 3 subjects in pure English. The entire syllabus will be covered by November, December, and then the revision 1 will start, and then the revisions 2 will start. Okay, so multiple revision rounds, entire coverage of 11th and 12th in pure English with your most top teachers in the country. All right, they are at affordable prices only, and the batch has just started and there is a new entry point coming in, so please check it out. That will be definitely helpful for you in the long run. So I hope you guys are ready, everyone. Yes, come on guys, full energy, call up all your friends. Yeah, Capto is live. So let's begin with the class, my dear warriors, right? So let's begin. Right, ready? So let's talk about electric flux first. Now before we talk about what is electric flux, we need to understand what is flux in general. Flux represents the flow of a quantity, flow of something, flow of something. So, for example, imagine these are some streamlines of water. Water flows from one point to the other, maybe in a river, in a canal, in a tube, in a pipe, whatever. And imagine I happen to take some cross-sectional area. So I will then say there is some flux. I will then say there is some flux of the flow of the liquid. So this is volume flux. This is some volume flux of that liquid, because some volume of the liquid is flowing through this particular given area, cross-sectional area. It is flowing through this given cross-sectional area. So this is volume flux of that liquid. So in general, anything flowing, piercing through something, we then associate the term flux with it. Like we have seen in our previous lecture on the channel itself. I'm pretty sure you would have seen it. In case you haven't, I'm just showing it to you right over here. Yeah, this was electric dipole, and before that we did potential and energy, and before that we did electric field and field lines. Yeah, please check it out. And yes, after every class I ask you to do the homework. Make sure you are doing the homework and putting out the answers in the comment section. The PDF, everything will be pinned in the description box as well as in the comment section. Okay, so keep solving the questions and yeah, answering the homework questions as well. Hi future, hi Anamika, good evening my dear warriors. Electric field lines also look very similar to the streamlines of a liquid flowing or a fluid flowing. The flowing of fluid, that's a 11th standard topic. In case you do not know or have forgotten, it's okay. But you can just imagine some liquid flowing through a pipe or a canal or something, a river or whatever. So, if a liquid is flowing with some streamlines, similarly, I can show I can show our electric field. I can show our electric field or any kind of field flowing like this in our space. This is our field. This is our field. It could be any kind of field. It could be gravitational field. It could be magnetic field. It could be electric field. Any kind of field. It doesn't matter. Maybe it pierces through some area over here. Maybe it pierces through some kind of area over here. And then I will say, yes, there is some kind of flux associated with it. There is some flux which is associated as it pierces through that area. So this field could be anything. This field could be gravitational field, gravitational field. This could be magnetic. This could be magnetic, or this could be even electric. It really doesn't matter. Accordingly, that kind of flux will be associated with it. So now that you understand what flux means, how do I know whether there is electric flux or not? The answer for that is simple. Say for example, I just take up some kind of an area over here. This is some kind of an area over here. I take some kind of another area over here. I take another area over here. So let's say the electric field is coming like this, going out. Okay, I'll just highlight these so that you are absolutely very clear what we are talking about. Just going to highlight them. So this is some random areas in our 3D space which we have chosen. And remember, to measure flux, we always need some kind of area, because a flux or field lines or any kind of lines will always pierce through some surface which will have some area. So we always need some kind of imaginary or physical area to measure the flux. So let's say the field line is coming like this and going like that. Field line is coming like this, okay, and going like that. Field line is coming like this, okay, and going like that. In the other case, what happens is the field lines are not going through that area. They are going from above it or below it, maybe like this. Nothing exactly is piercing it. They're just going above or below it, maybe, or from the sides. In the another case, maybe the field lines come like this and they go and they again come back for some reason like this. The field lines go like this, okay, and maybe they again go and hit back like this, and they come back from here like that. So something like this, something like this, okay. So in each case, let's understand whether there is some kind of flux or not. In the first scenario, 100% there is some flux through the area. There is definitely some kind of flux is there. So the symbol for electric flux or in general flux is phi. So here I will say phi is not 0. Because the flux is there, the symbol for flux is the Greek alphabet phi. Over here, because nothing is piercing through the area, that is the reason why I will say the flux is 0. That is the reason why I'll say the flux is basically going to be 0. Everybody till this point absolutely clear? Yeah. No, electric field, Arvind, has been already taught. Yeah. Okay, it's already been taught. My physics and unit test, electric potential, I'm pretty sure you will ace it. And yes, William, solve the tattva. It will definitely help you. Yes, I sure we are trying to complete everything, my dear. Okay. All right. Hi, Logi. Welcome aboard. The flux is 0, and the reason for that is nothing is piercing. Nothing is piercing the area. Nothing is piercing the area. Over here, a line pierces, but again pierces back in the opposite way. So whatever field or flux crosses this side again comes back to this side. So I will say that the net flux is 0, because whatever goes on to that side again pierces back over here. So that is the reason why the net flux is 0. So this is a very interesting case. A lot of people say, yes, sir, field lines are piercing, flux is there. Yeah, maybe in this region flux is there, But if you consider this entire area, whatever lines go, again they are coming back. So whatever is going out is coming back in. Hence, that is the reason why the net flux is 0. So now you might be getting an idea of how flux can be more, or basically how flux can be there or not there. So in general, I can then say, I can just say, just one second over here. In general, I can then just say that I have a small area uh, versus a big area versus that same area but more number of field lines. How does the flux change? Observe here, some number of field lines are passing. Here, what happened was, because the area increased, those field lines which were unable to pierce now are now piercing through that area, thereby increasing the flux. So here, if I say this is flux 1, this flux number 2 will be more than flux number 1, since area is more. Area is basically more. Can you see that? More number of field lines are piercing through that area. Here, those field lines missed piercing through that area. Let's say somebody in that same area increase the strength of the field. So instead of 2 lines passing through that area, we have even more lines passing through it. Even more lines passing through that area. So in this scenario also, flux number 3 will be more than flux number 1, because field is more, field is stronger. So in general, now I can sense that the flux depends on the area. It also depends on the field strength, basically electric field. Do you guys see this clearly coming through? So can I say that the electric flux, it is proportional to the field lines piercing that area? So the number of lines which are piercing that area, the number of lines which are basically piercing that area, what is that proportional to? That is definitely proportional to, the electric field and also the area, and also basically the area part of it. Also the area part of it. Perfect. But sir, I have an problem. I think there are certain situations where there will be field and area, but still flux will be 0. Can you think of that? Hi, Rangampeta, welcome. Yes, welcome, welcome. Yes, we are going from basics to advanced. Yes, definitely. So think about it. Think about it. What if the same area is there? What if the same area is there? Same field is also there as before, maybe. Same field is there as before, maybe. But the area is like this. Oh, then nothing pierces through this. And in this scenario, the flux in the fourth scenario will be 0. That means I have used a wrong word over here. It should not be and. I should put a comma. It depends on field, comma, area, and also the orientation. It also depends on the orientation. Orientation. It also depends on the orientation of how that area is basically oriented in each scenario. Here, the area was so oriented that the flux was able to pierce through it. But here, it is so oriented that the field lines are not piercing through it. So that is the reason why flux is 0. Hence, the orientation of that area matters. How does it exactly matter? For that, I have a beautiful visualization for all of you. Observe this carefully. The same sheet is vertical like this, and I tilt it. Can you see, the moment I start tilting, earlier these lines which were piercing this area are now beginning to miss that particular sheet, are beginning to now miss that particular area. Are you able to visualize and see it? In fact, those lines from below also, which were earlier piercing this big sheet, the moment I tilt it, gone, they are missing it out. If I tilt it more, they miss even more. And if I make it like this, then the lines are parallel to the surface. They will not pierce through it. It will look just like this diagram. And then the flux will completely disappear through that imaginary surface. How many of you visualize this? Yeah. How many of you? Welcome, Thor. Clear, Daniel. Hi, Salah. Yep. Great, great. Maxwell's first equation, not important right now. We are starting off with flux. The Maxwell's equation, we, basically are, they are just rephrasing the Gauss's law and Faraday's Lenz's law and all of that. Okay, we will see what is exactly Maxwell's law in the simplified form in the electromagnetic waves chapter. Okay. Complex circuits, it's still time is there, my dear. It's in current electricity. Okay. So it definitely depends on the orientation. So we now define a new thing called as the area vector. Observe this. We now define a new thing called as an area vector. And area vector is a vector which is basically perpendicular to the surface. It is a vector which is perpendicular to the surface. Right now, this is perpendicular, as you can see, to the surface, imaginary or real. So that is my area vector. Same way, if I tilt it, you can see that the area vector will make some angle with the electric field lines. So now my area vector is tilted somewhat like this. I hope this is visible slightly. Yeah, it is always going to be perpendicular to the surface. And now it has started to make some kind of an angle. It has started to make some kind of an angle with the electric field, angle theta with our electric field. So I think the theta has some role to play in calculating how much flux is passing through. Theta definitely has some role to play in calculating how much flux is passing through it. So how do I measure that? The answer is simple. The answer is simple. Let me show you how. Imagine this. Let me take this slide again. So it definitely depends on the orientation. So how do I decide that? See guys, see, imagine I take the side view of it, the same diagram, but I'm seeing the side view of it. Maybe it looks like this. So the area vector could probably look like this. So this is our area vector. Some books use the symbol S. I am using the symbol A. Some books will use S, some books will use A. It is irrelevant which symbol you use. Okay, either use A or S. Don't get confused. Okay, so this is definitely perpendicular to this surface. So this is basically a surface, and this is called as our area vector. Area vector is always going to be area vector. Area vector is always going to be perpendicular to the surface. That is how I define the direction of the area vector. Okay. Now let me show you the electric field lines. Let me show you the electric field lines. They are passing like this, like this, like this, and so on and so forth. I know one thing though. Whatever flux passes through this, where there is some angle made by the area vector and the electric field line. So what is theta? So theta is basically the between angle between two things. What are those two things? Area vector and the electric field. Area vector and the electric field. Whatever flux, count the number of lines, 3 lines are passing, same flux will also pass through another imaginary area which is exactly perpendicular like this. Just imagine another perpendicular area like this. So same flux will pass even through this. So if this is some surface which is right now let's say inclined, the surface is basically inclined. Imagine another surface which is basically perpendicular to the field. Imagine another surface which is basically perpendicular to the field. That will have the same flux as the inclined area. Are you convinced with this? Reason, same number of lines, whatever cut through this, have to cut through the inclined surface. So I can say that the flux phi through the inclined and the perpendicular surfaces surfaces are going to be the same, are going to be the same, are going to be the same. Everyone till this point? Yep. Very good. Very good. Very good. Awesome. Awesome. Now just imagine this. If I want to calculate that flux through that whatever surface I want, I will say I will measure the flux through the perpendicular surface. Flux depends on the field and area and the orientation part. So for that orientation part, that is why we are doing that derivation. We just saw if there is more field, there is more flux. If there is more area, also there is more flux. So 100% it is proportional to field and area. So can I just say in SI units, this flux will be nothing but the field multiplied by the area, the constant of proportionality being 1. Just like in Newton's laws, F is proportional to ma. In SI units, when mass is 1, area is 1, acceleration is 1, force is 1 Newton. So then, the constant of proportionality becomes 1. Same way, because the flux was proportional to the field and area, so I used SI units and I said let the constant of proportionality be 1. So it is field multiplied by that area which is perpendicular. Field multiplied by the area which is perpendicular over here. The field, of course, is E. What is that perpendicular area? Now that is the question. What is this much area? See, this much area was A. This perpendicular component, how much will it be? Well, use logic over here. If this is theta, then think about it, even this would be theta. How is that? How is that so? Just draw a line like this. If this is theta, this is 90 minus theta, this is theta. If this is theta, obviously this is also going to be theta. Between two parallel lines, these are alternate angles. So if this is hypotenuse, this is adjacent side for theta. It is obvious that cos of theta, which is adjacent side, will be nothing but the area which is perpendicular upon that original hypotenuse which is having some value of A. This is going to be A, this is going to be A perpendicular. So cos theta is adjacent by hypotenuse, adjacent by your hypotenuse. So what is that perpendicular area? It is A cos theta. So I can just put it is nothing but A multiplied by cos of theta. So that is the value of the flux. So the flux through the inclined surface and the perpendicular surface were same because same lines are cutting through. The flux through the perpendicular one is easy to calculate. I can just say it is field into area. There is no question of orientation. Every line is passing through it. Nothing is missing through it. So field is E, area is this much. So I use trigonometry over here. Cos theta is adjacent by hypotenuse. Hypotenuse being A, okay, that is that area. This will be nothing but A cos theta. That's it. So E into A into cos theta. But wait a minute, field is a vector. Area, I just defined it as a vector. The output is a scalar quantity and cos is also there. So I am reminded of the chapter of vectors where we had defined the multiplication of two vectors giving the result as a scalar quantity. That is then called as a dot product. So I can just write this as phi is equal to the dot product of the electric field with the area vector. The dot product of the electric field with the area vector. Is this absolutely clear, my dear students? Yep. Everyone? Awesome. 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 Okay. Great. So keep this in mind that flux is going to be a scalar quantity. It is going to be a scalar quantity. If you ask me the unit, what is the SI unit? What is the SI unit of flux? See, field has the unit of volts per meter. Area has the unit of meter square. So when you cut meter, it will become volt meter. So volt meter is the SI unit of flux. A lot of students have heard them saying Weber. That is not right. Weber is the unit of magnetic flux, which is completely different. Okay, so electric flux, the unit will be voltmeter. You can also convert it into Newton per coulomb into meter square. That is also fine because field can be also written down as Newton per coulomb. Okay, that is also perfectly fine. So electric flux is a scalar quantity which is the dot product of electric field with area vector, which can be also simplified as EA cos theta, theta being the angle between area vector and the field vector. Area vector is a vector defined as the you know uh, uh, it's pointing in the direction perpendicular to the surface and has a magnitude of the area itself and has a magnitude of the area itself. Great, great. So that is electric flux. There is an issue. The issue is every time our areas may not be so cool, so straight, they could be curved, and even the field may be non-uniform. So what to do in such cases? So let's have a look at it. Imagine you have some kind of a surface like this. Okay, it's some three-dimensional curved surface. It could be anything, guys. So this is our curved surface like this, and even the field through it is not constant, it is non-uniform. So that means the field lines are curved lines. So some lines are going like this, some lines are going like this, some lines are going like this over here. So everywhere, as you can see, the field lines are curved in nature. Okay, so it is basically a non-uniform field passing through passing passing through a curved surface, passing through a curved surface. Can I measure the flux through a curved surface? The answer is yes. So if I want to measure the flux through any curved surface, the answer for that is simple summation, which is integration. You take small areas. Yes, you take small areas. Let's say you take some area over here, and that will have some small area vector, maybe like this, maybe that has a small area vector, which I can call it dA. So dA is nothing but an elemental area vector. It's an elemental area vector, and at that location, the electric field at that particular location, the electric field happens to be, let's say, E at that location. E is the field at that location, at that location, at that location. Maybe there is also some kind of an angle between them. Maybe it is theta, that theta will also keep varying. So the small flux, over there, so the small flux, so the small, I can put it over here only actually, the small flux d phi will be nothing but the electric field at that location dot producted with the area vector. The electric field dot producted with the area vector will give me the flux in that small area. Now, electric flux being a scalar quantity, every small area I can calculate the flux. Small flux, if I keep on adding it for the entire surface, I'll be able to measure and calculate the net flux. So the net flux, which is on the curved surface, will be the sum of all the flux through such elemental areas, through such elemental areas. Because we are talking about sum of small numbers, that process is called integration. So it will be integration of, so the flux through the curved surface will be the integration of nothing but the electric field dot dot area vector, that is the answer for it. So let me block this off. This is just for a curved surface, it will just become integral, nothing else. So for a flat surface, it was EA cos theta or just E dot A. So when there is a curved surface or field is different, you will take small areas and you will try to integrate it over the entire thing. Is that right? Everybody with me? Clear? Okay. Now there is another doubt which many students ask. Sir, if I have some area like this, and let's say the field is going over here, let's say the field is going towards my right side, and you are saying area vector is going to be perpendicular to the surface itself, then I can draw the area vector here also. I can draw the area vector like this also. Both should be correct. Technically, both are right. If I show the area vector here versus the area vector here, both are definitely correct. Do you guys understand that? But then what to do in such scenarios? This is also going to be perpendicular. Okay, this way or that way. In this case, you will notice the angle between area vector and the field is 0. In this case, the angle between area vector and the field is 180 degrees. So here, if you calculate the flux, it will be nothing but EA cos 0. Cos 0 is 1. So it will be nothing but positive EA. It will be nothing but plus EA. That will be the flux. But here, if you calculate the flux, it will be EA cos 180. Cos 180 is minus 1. So the flux will be negative EA. Oh, so the flux is just same in magnitude, but opposite in sign. So what does this tell you? It tells you if you choose an area vector, the choice is completely yours, and the flux comes out to be positive, that means the field is passing in the same direction as that of the direction of the area vector. So for suppose example, there is some area like this and I take the area vector this way and the flux comes out to be positive value. It means electric field line is going in the same direction. If by chance the flux comes out to be negative, that means the field lines are going opposite in direction. That is the only significance. Okay, so the positive flux, so the positive flux means that the field is in same direction of the area vector. Okay, that is the meaning of positive flux. It's in the similar side, it's going on the same side. But the moment it is negative, so negative flux just means the field is against the area vector, That is the meaning of it. Sir, but this will create confusion, no sir? Because somebody will take this side, somebody will take that side. So who is right? Magnitude, I agree. Both of them will get EA only. But sign-wise, both of them will be wrong. Both of them will be opposite. So the answer to that is, don't worry about it. Both of them are right in their own way. Just like in kinematics, somebody might choose right side to be positive. Somebody might choose left side to be positive. It's completely a free hand. It's a matter of choice at the end of the day. But there is a but over here. What is that but? The but is the moment you have a closed surface. Yeah, the moment you have a closed surface. Let me see if I have a closed surface somewhere around me. Yes, I do have a closed surface around me. Yeah, see this pouch. This is my microphone pouch. Right now it has an opening. Can you see that? It has an opening. It's an open curved surface. But the moment I pull these strings, it's now a closed thing. There is some air trapped in it, maybe. It's a closed surface. Yeah, getting my point? So this is a closed surface, but if I open its mouth, things can go inside of it. things can go inside of it, but I can just pull these strings and it's now become a closed surface. Okay, perfect. So the moment I have something like a closed surface, I have something like a closed surface. Just one second. Okay, this is something like a closed surface, some three-dimensional thing. So this is our closed surface. The convention is always choose the area vectors outwards. No matter where you are, the area vectors have to be chosen outwards only. Area vectors have to be chosen outwards only. Very, very important. The area vectors outside have to be chosen. That's standard. So for a closed surface, which is now also called as a special name, it is called as a Gaussian surface. Any closed surface is also called as a Gaussian surface, that is synonymous with it. So whenever you hear the word Gaussian surface, understand what they are meaning is just another way of saying the surface is closed. So for a closed surface, the area vector, the area vector has to be pointing outward or outside. It has to point outside, the area vector. This is very, very important. Which also means that if there is any field which is coming like this, so that will be positive flux. But if there is any field which is going in like this, that will be considered as negative flux. So negative flux goes inside the surface, whereas positive flux comes outside. The positive flux comes outside. This is by pure sign convention, because if the flux is positive, that means field is in the same direction of the area vector. So area vector being outwards, so the flux is positive means the field is also coming outwards. If it is negative flux, that means the field lines are going inwards inside the closed surface. Are you able to visualize this? Yeah, everyone with me? Yep. Sir, can we write flux formula in integration form? Yes, Gitika, that's what we just did. Thank you, Daniel. All right. Whole thing, right? Or start something, concepts for 2027. Run, Rohin, I didn't get you. You are writing 2027 as in like you're writing for 2026, the concepts of 2027. Oh, you mean the 11th standard lectures. Obviously, you have to do it from the scratch, especially the mechanics part. Mechanics is the most important part of 11th standard physics till SHM. Simple harmonic motion, rotation, gravitation. Okay, do everything properly. That is the most crucial thing. Fluids, thermo, waves and all that, you can do it later on also. I mean, that will not take you much time. Yes, yes, Sumedha, we just did elemental integration. Yeah. Yeah, we are going to do some problems also. Yes, Gitika, definitely. Okay, fair enough. So now that we have written this down, let me do some questions on this. Okay, there is a cylinder. There is a cylinder of radius r and length L, which is placed in a uniform electric field E, which is acting parallel to the axis of the cylinder. What is the total flux over the curved surface area? So let's just visualize how that cylinder might look like. Okay, so this is our cylinder, maybe like this. Okay, okay, like this. And the electric field lines are parallel to the axis. So that means they come like this, they go from here. They come like this and they go from here. They come like this and they go from here. So this is how the field is. The radius of the cylinder is mentioned, which is r. The length of the cylinder is also mentioned to be L. So question is, what is the total flux over the curved surface area? Guys, the total flux through the curved surface area they have asked. Look at it. It's placed in a uniform field and acting parallel to the axis of the cylinder. If you notice carefully, the curved surface area is this. And if you take any area on that curved surface, the small elemental area dA will be like this. The small elemental area dA will be like this, whereas the field at that place will be in this direction. This is the direction of the field. So if you notice carefully, the angle between the area vector and the field vector is 90 degrees. So cos of 90 degrees is 0. That means the flux will be 0 everywhere, everywhere, everywhere on the curve, everywhere on the curved surface, everywhere on the curved surface, no matter where you take that area. Even if you take that area vector maybe somewhere over here or maybe over here like this, understand in that particular plane, that area vector will be perpendicular to that particular field. So everywhere the flux is 0. So the net flux must be option D, which is 0, which is absolutely right. Which is absolutely right. Not just the curved surface. In fact, what would the answer be instead if it was said what is the total flux through the cylinder, not curved surface, cylinder? Then what would happen? This flux is going inside. So this will be negative flux, which will be negative E into the area. Area is basically pi r square. On this side, it will be positive flux and it will be positive field multiplied by area, which is pi r square. So if you ask me what is the total flux through the entire cylinder, it will be flux through the face 1, through face 1 plus flux through the face number 2 plus flux through the curved surface. Flux through the curved surface. Through face 1, it is nothing but negative E pi r square. Through the secondary phase, it is positive E pi r square. And through the curved surface, there was no flux at all. It was 0. We just saw it. So hence the total answer will be 0. So that answer would also be 0. And anyways, you can see whatever comes inside goes outside. If whatever comes in goes out, the net flux should be 0. Does that make sense to all of you? Yes, everyone. So that would also be 0, guys. So if I have any kind of curved surface like this, a closed surface, sorry, like this, if whatever line comes in eventually goes out, whatever line comes in eventually goes out, whatever line comes in eventually comes out, whatever line comes in goes out. So if whatever comes in is going out, then basically the negativity is equal to the positive flux. Hence, you will see that the net flux in that closed surface will be 0. Is that absolutely clear, my dear students? Everyone? Yeah. Sir, the elementary area of all the lines are equal. Yes, you should take dA as a, you can say, same area. dA will be same everywhere. Yeah, that dA is, a smallest possible area. You cannot really compare dA of this versus dA of this. It's so small that you don't worry about what is the size of dA. It's close to 0, but not 0. It's like a point. So you cannot say this point is bigger than that point. It is meaningless to compare such things. Yeah. Okay. Fair enough. Let's go to another question coming up on your screen. The electric field in a region of space is given by E naught I cap plus 2 E naught J cap, where E naught is 100 Newton per Coulomb. The flux in the circular surface of some radius parallel to the YZ plane is, interesting, YZ plane. This is X, this is Y, and this is Z. And our circle is basically in the YZ plane. So if it is in the YZ plane, that means it should be like this, I believe. Something like this. This should be our circle. The area vector for this, would be over here. This would be the area vector for that particular circle. Where is the field? It is in I cap and it is also in J cap. Now this is very interesting. See, there is some field which is like this, which is basically, I can say, E naught I cap. There is also some electric field which is going like this, some electric field which is going like this, which is 2 E naught J cap. Now you guys think and tell me carefully, out of the I cap and the J cap component, which component will contribute in the flux? Think logically. Which component will contribute in the flux? 100% it is the I cap or the X component, because that is the field which will exactly pierce through this area, but the J cap will not pierce. So this will not contribute, in the flux, since it is not piercing. It is not piercing. But this will contribute, contribute in the particular flux calculation. So once I want to calculate the flux will be this field E naught is exactly in the same direction as that of the area vector. So the angle between them is 0 technically. So cos 0 is 1. So what is the value of E naught? The value of E naught is basically 1000. It is clearly mentioned over here. What is the value of the area vector? Well, it is pi into r square. Is the radius mentioned? Yes, it is 0.02. So 0.02 whole square. And cos 0, of course, is 1. So yes, that's it. We have over here all the numbers. You can see automatically we can get the answer. So this will be nothing but 10 to the power 2. Pi is nothing but 3.14. 0.02 square. So 2 square is basically 4. This will be 10 to the power minus 4. Is that right? So this will be 3.14 multiplied by 10 multiplied by 4 multiplied by 10 to the power minus 2. Now 3 fours are 12. Yeah, 3 fours are 12. So I'm guessing around this, what we'll get is 12.5 into 10 to the power minus 2, which is 0.125 Newton per coulomb meter square. That's it. So 0.125 Newton meter square per coulomb. That should be the answer. Is this absolutely clear, my dear students, how we calculated it? One component didn't even pierce, and this same diagram I have also given it to you over here. Where is it? When I explained it to you, the concept of orientation. When I explained it to you, the concept of orientation, right over here. Here the flux is 0 because the area vector is perpendicular to the field vector. That's it. Nothing, no flux is there. So only contribution will be there when the field lines actually pierce through it. Okay, that is what we have seen. Okay, perfecto. So that is also done. Okay, perfect. I think now we have some Gauss law problem. So let's go to the next concept. Yeah, so that was the field calculation. We can do one more question on the curved surface concept. This kind of question is also very, very common in JEE Mains, especially, or even in JEE Advanced sometimes. So the concept goes like this. 1 second, guys. Are you? Okay. This is okay, got. So there could be maybe a question something like this where you might have some x-axis, some y-axis, and some z-axis, and maybe there is some surface like this over here. There is some surface like this over here, okay, and maybe this is having a side length of A, this is also having a side length of A, and it is given to you that the electric field which is there, the electric field which is there, is maybe something like this: 2y square, 2y square I cap plus 7x j cap Newton per coulomb. Okay, this is a very good question. And the question is, can you find the net flux? Can you find the net flux through that area whose square side length is A? Okay, very nice question. Can you find out the net flux through this? Now, as you can see, the field depends on the x and the y coordinates. That means it is definitely a non-uniform field. This is x coordinate, this is y axis, this is z axis. One thing is clear, out of I cap and j cap, because the area is like this, the x component, which is the I cap component, will pierce through that area, but the j cap component will be parallel to the area. So it means that this particular portion, which is there, this particular portion is parallel to the surface, that is, it doesn't pierce it. If it doesn't pierce it, there is no flux contribution. I have also seen some students make a mistake over here. When I say that the electric field is in the j cap direction and it is parallel to the surface, they think parallel means theta is 0. So if theta is 0, then cos 0 is 1. So how come it is 0 flux? See guys, don't make this mistake. When I say that the electric field is in the j cap direction, this is some electric field in the j cap direction, and I'm telling you that it is parallel to that particular surface. It is parallel to that surface. It is actually perpendicular to the area vector. So don't get me wrong. It is actually perpendicular to the vector of the area, but parallel to the surface of that same area. So two confusing things, lot of students make a mistake. Always read the statements carefully, whether they are given the angle with the area vector or the surface itself. So this is the surface. So for the surface, the field is parallel, but for the vector area, it is perpendicular. So if you even do cos of 90, so even if you do cos of 90, obviously cos 90 will be 0. So hence there is no flux due to this part. So I can just get rid of this part of the problem. I don't even have to worry about it. So my next step will be, let me just forget this part of the problem. I'm not even interested because that is irrelevant for my solution. Electric field is 2y square I cap. So it only changes with the y coordinate and it is in I cap direction. That means in the x direction, which means, see, if the y coordinate is 0, this is 0. So electric field is not there. As y increases, electric field increases in the x direction, meaning I cap direction. So maybe, I'm just saying maybe, the electric field might look like this. Chuma, I'm showing something over here. As you go up, maybe the strength of the field might increase. As you go up, the strength of the field might increase. Something like this. Just visualize this. Something like this. As you are going up, the flux or the field strength is slowly, gradually increasing. Are you able to visualize? Hi, Gaurav. Yep. Yeah. You can't really count the number of lines. That number of lines concept is just for your visualization purpose, but you know, number of field lines can be infinite. So you really can't count infinity. So if it is like this, I have an idea. Why not take small strips in this manner? Why not take small strips in this manner, like this, and find the flux through a strip like this, not vertical, horizontal, because everywhere on a horizontal strip, the field is the same. So what I am considering now over here is, imagine this particular area over here like this. You just worry about, you just worry about small strip of area like this over here. Maybe it is at some coordinate y. It is at some coordinate y. Maybe the thickness of it is dy. The length of it, the length of it obviously will be this one. It will be nothing but a. And the field everywhere on this particular line, it will be like this. It will be like this. And let's say it is E. The magnitude whose value is given over here, it is nothing but 2y square Newton per coulomb. Oh, so why not calculate the flux through that strip, the flux through that particular strip. The flux through that particular strip will be d phi. It will be nothing but the field multiplied by the area of that particular strip. The field at that place, the field at that place is 2y square. The area of that strip is height into length. Length is basically a, height is nothing but dy, so that is d phi. So therefore, if I want to find the net flux will be integration of these d phi's. So therefore, I have to add all those fluxes. So what will happen is I will get that 2y square a dy over here. Out of that, I can clearly see that number 2 and number a is a constant. So only y square and dy will be there. Limits of the integration. My y coordinate will start from 0 and go till a height of a. As you can see, this is also going to be a. So it starts from 0 and goes till a. So what is the integration of this? So 2a, y square's integration is y cube divided by 3. Limits of the integration have to be substituted still over here, which is 0 and a. So once you do that, you're just going to get 2a, and you will have a cube by 3 minus 0 cube by 3. So as you can see, a cube and a, when you multiply, it will become a raised to 4. So it will become 2 by 3 a raised to 4. 2 by 3 a raised to 4. That is the answer, guys. 2 by 3 a raised to 4. Yep. No, Mitty, you cannot get access of the Sigma batch. Even if you're a pro student, Sigma batch is a completely different batch. No matter which batch you are in, you cannot access Sigma batch unless you are enrolled in the Sigma batch. Okay. Is this clear? Did you love this question? Everybody with me on this? Yeah. So we just had to integrate the small flux which is passing through this small strip. Each strip will have a different amount of flux. So I need to add up by integration. The limits of the integration will start from the y coordinate being 0. That means the lowermost strip till the uppermost strip whose y coordinate will be a. Okay, that is why the limits of the integration. Cool. Shall we go ahead now to the next part? And that is basically nothing but our Gauss's law. Okay, Gauss law. And Gauss law is very straightforward. See, I'll tell you something very simple. I'll tell you very simple, guys. Imagine, just imagine that we have some positive charge over here. We have some negative charge over here. And let's say we consider some closed surface like this. We consider some closed surface like this. We already know how the field will look like due to a positive charge. The field due to a positive charge looks something like this. They come radially outwards. They come radially, basically outwards like this. Second, radially outwards like this. Okay. Oh, sorry. But for negative charge, it is radially inwards. My bad. For negative charge, it will be radially inwards like this. Only for a positive charge, it is radially outwards. Now, if you ask me what is the flux through this shaded area, closed area, 100%, I will say this particular flux number 1 is a positive number because the flux is coming out. If you ask me what is the flux through this curved area, shaded area or that closed area, then I will say the flux through this particular area is 100% there, but it is negative because the field lines are going inside that closed area. I just gave you the sign convention of it right over here. Flux coming out positive, flux going in is negative. That is our sign convention, my dear students. So coming back over here, I can clearly see here we have positive flux, here we have negative flux. Something to keep in mind. Let me play with this further. What if I chose another surface, another random shape like this over here versus another some random shape like this, again a closed surface. If you ask me what is the flux through this surface, let's say phi 3, I will say it is still positive and not just any positive. In fact, it should be same as phi 1. Why is it so? Because the same line cutting here is cutting here. Same line cutting here is cutting here. Same line cutting here is cutting here. All the lines cutting the light pink surface are cutting the dark pink surface over here. And what did I just say when I told you everything about flux? Electric flux, where is it? Electric flux is always proportional to, electric flux is always proportional to the field lines cutting, piercing through an area. If by chance the field lines are the same through any area, then I will say the flux is also the same. So over here also, I can say that the flux of the dark pink is the same as the light pink because same lines are cutting. Same logic I can apply here. I don't care about the shape. It could be any random shape. But here also, this flux 4 will be not just negative, any negative because it is going in, but it will also be the same as phi 2. It will also be the same as phi 2. Everyone with me on this? Okay, sir. Another interesting concept. Another interesting concept over here. If by chance somebody chooses a surface over here, somebody chooses some surface like this closed surface over here, whatever flux goes in is also coming out. Going in is coming out. We just did a question on it over here somewhere. We just did a question on it somewhere. Yep, I think over here. I just told you if going in and coming out is equal, the net flux 100% is going to be 0. So using this particular logic, can I just say the flux through this fifth surface is just going to be 0 because whatever is going in is also going out. The same logic I can use over here. Whatever goes in goes out. Whatever goes in goes out. Whatever pierces in pierces out. Negative flux is positive flux. So the flux through this surface number 6 is 0 because whatever goes in is also going out. Oh, interesting. Very nice. One more thing, and this is the last thing over here. Imagine somebody just increased the value of this charge, or somebody just changed the value of this particular charge. Somebody made it more positive. Somebody made this more negative. What will just happen? The only thing that will happen is just that, the number of field lines will increase, of course. More number of field lines will come because more charge is there over here. So if more field lines come in, more field lines exit out from here. If more field lines are going to come out like this, if more field lines are going to come out like this, then I will say that this flux 1 will increase. It will increase. Here also this flux 2 will increase in magnitude. Will increase in magnitude. Definitely it will increase in magnitude because more charge was present inside. So from all these things, one thing is very obvious. If you have a closed surface, which is also called as a Gaussian surface, like I have told you before over here, any closed surface is also called as a Gaussian surface. I am saying that the flux through that closed surface depends on the charge which is there inside. If it's a positive charge, it is positive flux. If it's a negative charge, it's negative flux. If the surface is big or small, doesn't matter, as long as the charge is inside somewhere, that's it. The flux will only depend on the charge present inside. Where it is located doesn't matter. But what matters is how big or small that charge is. If it is a very big charge, more flux will come out, or if it is a small charge, very less flux will come out. Also, I am seeing if there is a surface which does not contain any charges, then also there is no flux in it. Sir, what about a positive and a negative charge inside? Well, let me show you. Imagine there is a positive charge here, there is a negative charge here. Okay, and we all know how the flux or the field lines looks like. The field lines look like this. We have seen this, in the previous sessions, right? This is how the field looks like. You will have more field lines obviously coming like this. Now imagine somebody chooses a surface over here, doesn't matter. This flux will be 100% positive. If somebody chooses this particular surface over here, 100% this flux will be negative, because you can see the field lines going inside over here. If somebody decides to choose a big surface like this, well, that flux will 100% be zero, because whatever goes out will come in. Whatever goes out will come in. If somebody decides, okay, boss, I'm going to choose some surface over here, it does not include any charge, that flux is also zero. From all these observations, it is very clear that that the flux through a closed surface through a closed surface depends on depends depends on what and all does it depend on? The charge present inside. The charge present inside. Okay, the charge which is present inside. And it doesn't depend on and it doesn't depend on it doesn't depend on it doesn't depend on what does it depend on? What doesn't depend on? The placement of the charge. The placement of the charge, where the charge is, doesn't matter whether the charge is here or here, as long as it is inside, that's it, done and dusted. Also, the flux does not depend on any charge which is present outside, like you saw over here also. For this surface, this charge was outside, it doesn't matter. So the charges outside do not matter. So the charges which are present outside do not matter. So the charges which are present outside do not exactly matter. So only the charges which are inside matter. So from this, Gauss was able to formulate a principle. Gauss was able to formulate a principle, and he said that the flux through a closed surface is directly proportional to the net charge which is present inside. The net charge which is present inside. But then he said, in SI units, that constant of proportionality was found to be basically 1 by epsilon naught. So that is your permittivity of free space. So that constant of proportionality is 1 by epsilon naught. So this becomes basically your crude or basic statement of your Gauss's law. We will make it even more formal in a bit. Okay, so the net flux in a closed surface is 1 by epsilon naught times Q inside, that net charge present inside, not on the charges outside. This is a very basic form of writing the Gauss's law. But I think we can write this in a slightly better form, because if you have any curved surface, if you have any curved surface, we have just seen how do we write the flux in integration E dot dA, right? So the same thing, let's do it over here. Say for example, oops, second. Okay. So for example, these are our field lines, maybe like this, maybe some are going in, who knows? Something like this. These are the field lines, and at any random place, you have our dA vector, our small area vector, and we have our electric field at that particular place. So the flux through the closed surface, I will write it down like this: integration of electric field dot producted with the area vector, which will be equal to the total charge which is present inside, the whole thing divided by epsilon naught being the permittivity. Remember the value of permittivity of free space, whose SI value is 8.85 into 10 to the power minus 12. 8.85 into 10 to the power minus 12. That was the value of it in SI units. So this integration, I will have to be slightly be careful. I will have to measure every single area. And in mathematics, when we don't want any area to be left out, I want all the area to be covered. It's like, you are instructing someone, clean the entire room or paint the entire room. It's a very specific instruction as compared to paint a wall or paint the ceiling or clean the floor. It is just one surface versus the entire surface. Nothing should be left. Then we put this as a symbolic notation, which is called as the closed integral, closed surface integral, that signifies cover the entire surface. So this is our closed or basically Gaussian, surface. Closed or basically Gaussian surface. So it only depends on the charges which are present inside. Charges which are present inside divided by epsilon naught. This is very, very important. So this is now the final way in which we can express our Gauss law. Cyclic integral, closed integral of electric field with area vector is the net charge inside by epsilon naught. Now the funny part about this integration is that the value of this integration depends only on the charges inside. It does not depend on the charges outside. Yeah. So very, very important thing which I am telling you, the integrations value, the total integrations value depends only on inside charges, But there is a big but over here. What is that big but over here? But the electric field which is there, the value of this integration only depends on the charges inside. But that electric field which is there, that depends, that particular thing, that depends on both inside and outside charges, both. Yes, both inside and outside charges. This is very important concept, guys. This value will depend on whatever charges are present inside and maybe some charges are there outside also. These are outside charges. These are outside charges. These are basically inside charges. So this field will depend on both, but the value of the integration, the summation, only depends on the inside charges. Kind of makes sense. Just look at this. I mean, see, take this example only. If you say the electric field at this point, it is because of the positive charge and the negative charge both. It is the sum of both those electric fields. The positive charge is giving some electric field, the negative charge is giving the electric field. These field lines are the net electric field lines. Guys, get it? So these electric field lines are the net electric field. Whether you choose the Gaussian surface or you don't choose the Gaussian surface, those field lines would exist in spite of you not choosing or choosing. Okay, so those field lines were dependent on all the charges. It's the net electric field lines. But when you integrate them, the answer only depends on the inside charges. That is the funny thing about Gauss's law. Is that absolutely clear? Thank you so much, Vijay. Yes, I'm so glad. 11th standard student waiting for Namrata's lecture but couldn't find it. Not sure why you couldn't find it. If the charge is positive and is not equal to negative, then there is more positive flux than the negative flux. Like in the previous example over here, or let's say if I just make a new example over here, something like this. Maybe here you have more positive charge versus negative charge. Then what will happen? You will have very few lines going on to this. You will have very few lines going on to this, and a majority of the field lines will go like this. Now, if somebody happens to choose a Gaussian surface like this, just visualize there are more number of lines going out than more number of lines going in. I mean, you can just count it also and see it. Very, very obvious. So there are more lines which are going out versus the number of lines which are going in. So you will see that the net flux will be 100% positive because the total charge is also going to be positive. So if you count the total charge which is inside, that is more positive than being negative. So you can see it will be more positive than being negative. Some of the charges might just end up being cancelled. They cancel out each other. So net charge is positive. So flux is also positive. As simple as that. As simple as that. Is that absolutely clear? Yes, Mayuri. Welcome, everyone. Okay, perfect. So maybe let's do some questions based on this. Here it comes. 5 charges are there situated in this diagram. This was JEE Mains 2024 question. The electric flux due to the configuration through this imaginary surface S is how much? Okay, so that imaginary surface, as you can see over here, this is that surface which they have marked. The question is, through this imaginary surface, can you guys quickly figure out what is the total flux? The flux through any closed surface is the total charge which is inside by epsilon naught. Okay. What is the charge which is present inside versus outside? I think this is outside, so don't count it. This is outside, so don't count it. Only count this guy, and this guy. Right? These are the only 3 charges which are basically inside this surface. So it will be nothing but 5q plus q minus 2q. Take the sign of the charges also, or else you will make a mistake. So 5 plus 1 is 6, 6 minus 2 is 4. So 4q by epsilon naught. So 4q by epsilon naught is the option number D. Option number D. Is this clearly understood how to solve these kind of questions? Very straightforward, guys. Perfect. Amazing. Let's do another question coming up on your screen. Here it is. Yeah, we have a question over here. A uniform field passes through a hemispherical surface of some radius as shown in the figure. The net flux through the surface is how many times of pi? Very interesting. A uniform field passes through a hemispherical surface as shown in this particular figure. So what is that basically flux passing through that surface in terms of pi? I'll tell you one thing, whatever flux will pass, whatever flux will pass through the circular base, observe this carefully now through the diagram only, that same flux will also pass, that same flux will also pass through the curved surface. Just see it and convince yourself that that is true. Yeah. Whatever flux passes through the curved surface will also pass through the circular base. Same number of flux. Why is it so? Can you convince yourself why it is true? Why it is true? Just look at some of the field lines. Just look at some of the field lines, guys. It is very obvious. This is going in, and the same field line is coming out over here. So this has no contribution only in the flux. But if you notice, whatever flux is going over here, whatever flux is going over here, that same flux magnitude wise is also coming out from here. That same line is also coming out from here. You can see that. That same line is coming from here. So the number of lines cutting through the circular base is the same as the number of lines cutting through the curved base. So can I say that whatever answer we want, the net flux through the hemispherical surface. So through the hemisphere is exactly equal to the flux through the circular base. Flux through the circular base, magnitude wise, of course. We are talking about magnitude wise only. Yeah, magnitude wise, it is the same. Whatever flux goes to this base also goes to the curved surface. Everyone? Yes. Hemispherical means a sphere's half part is a hemisphere. The half of a sphere is a hemisphere. Something like, by coincidence, I have a helmet. It looks like this. A hemisphere is like this. Yeah. It has a circular base over here. So this is like a hemisphere. Okay, perfect. So what is the flux through the circular base? It is nothing but the field. It is nothing but the field multiplied by the area multiplied by the cos of theta. What is the field? I think the electric field is already mentioned, which is nothing but 500 multiplied by the area, which is nothing but pi multiplied by radius square. Radius is 1.2 cos theta. Now that you need to be little bit careful. See guys, this one is the area vector. So the area vector is basically like this. If this is 53 degree, obviously the field with the area vector, the field with the area vector is making 37 degrees, as you can see over here. This is the electric field line. This is the electric field line. The electric field is making 37 degrees because in the question it was mentioned this is 53 degrees. You can see that it was mentioned in the question. I don't know whether you are able to see it. It is very light because I shaded it. It became very faint now, but it was 53 degrees. So it is nothing but cos of nothing but how much? 37 degrees, angle between area and the field. So now this is straightforward. So 500 into pi, 1.2 is nothing but 1.44 cos 37. What is cos of 37? That is nothing but 4 by 5. That's it. So do the math and you will get the answer. This 1.44 cancels, this 5 also cancels. So it will become 144 multiplied by 4 multiplied by pi, which is going to come out to be 1440 or almost. Just check this out, or no. Just see. No, it will not be 1440. 144 into 4, guys. Just do the math. 5 and 5 cancelled. Yes, because that was 5. This was 1.2. So 12 square, I've just done it as 144. So just do 144. 144 multiplied by 4. That's it. So I think, how much will it be? 14 4 and 4 16 560 and 14 576. It should be 576 pi. Just check this out. 576 pi. That should be the answer. Everyone? Okay, perfect. All right. Awesome. Awesome. 576 pi is the right answer. Let's go to another question coming up on your screen. Here it is. A hollow cylinder has a charge of q coulomb within it. phi flux is associated with the curved surface, the flux linked with the plane surface is how much? Very nice question, guys. Think about it. So imagine this is our cylinder, which is like this. Imagine there is a charge Q which is inside. Obviously, it will give some electric field everywhere like this. It will give some electric field like this everywhere. Some field will even pass through the flat surface from both the sides. They have mentioned the flux through the curved surface is some value phi. How much is the flux through the plane surface? One thing is very clear. The entire flux through the cylinder by using Gauss's law, can I say it is the charge which is inside by epsilon? The charge which is inside is Q, so it will be Q by epsilon. But the total flux of the cylinder will be the sum of three fluxes. The flux of this face, the flux of the curved surface, and the flux of the other flat face. So it is a flux of those flat faces 2 times plus flux of the curved face. So the flux of the curved face is already given to be phi. The two flat faces, I do not know how much it is. This is equal to Q by epsilon naught. So therefore, 2 times the flux of that flat surface will be Q by epsilon naught minus phi. Therefore, the flux through the flat surface will be 1 by 2 times Q by epsilon naught minus phi. So, half times Q by epsilon naught minus phi, that is option A, of course. That is the right answer. So, we started off with Gauss's law. We started off with Gauss's law. This is one of the beautiful application where we found out the flux, how much it is there through the flat surface, because we knew the total flux should be Q by epsilon naught. And this curved part was already mentioned. This curved part flux was already mentioned. Is that right? Yes, MPPS, the notes are already given to you. So after every class, you will see it in the description box here, or maybe even in the comment section, it will be pinned. Okay, but that will take a day or so. Awesome. Perfecto. Perfecto. Kavita, welcome, 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 my dear. Okay, next question. This particular question. Now, this particular question, I'm going to give you as a homework. I'll tell you why. Okay, this is a very interesting question. Homework. I will make you solve a very similar question right away, right now. Okay, we'll solve a very similar question just like this right away, right now. Okay, it is very much similar to that. Imagine there is a cube. Okay, imagine there is a cubical surface. Imagine there is a cubical surface. So let me just draw a cube like this. Okay, imagine there is a cube over here. Maybe we can. Imagine this is a cubical surface, and what happens is I have placed a charge. I have placed a charge exactly at the center. Charge Q is basically at the center of the cube. If you ask me, what is the net flux through the entire cube? I will say it is the same as the flux through a closed surface, because cube is a closed surface, and by Gauss's law it should be inside charge by epsilon naught. This is as per our Gauss's law, and the total charge inside the cube is only one singular charge, so it is Q by epsilon naught. So the flux through the entire cube will be Q by epsilon. Simple, straightforward. But let's say I become little greedy and I ask you, can you guess and tell me what might be the flux through any one of the faces of that particular cube? what might be the flux through any one of the face of that particular cube. Then I will think a little bit and I will realize, oh, wait a minute, there are 6 faces for a cube, and whatever flux goes up, down, front, back, left, right will be equal. So it will get distributed equally. So the flux through a face will be 1/6 of the net flux through a cube. This is completely by symmetry. This is completely by symmetry. So therefore, this should be Q by 6 times of epsilon naught. That is the flux through the face of that cube. So 1/6, 1/6, 1/6, 1/6, 1/6 everywhere. So total will be Q by epsilon naught. Everybody understands this? Perfect. Okay. Now I make this problem even slightly more crazier. How? Imagine now the charge, that particular charge is at the corner, of that particular cube. And now I'm interested what is the total flux through that entire cube? What is the flux through that entire cube? It's just at that corner. So how much flux is going through that cube? So if I try to visualize it, I understand one simple thing. If I draw the field lines like this, I draw the field lines. The field lines will go like this. It will also go like this. It will also go like this. It will also go like this over here. It will also go like this over here. They will also go like this over here. So they will be in all sorts of directions. Just visualize this in 3 dimensions. Oh, yes, sir, I'm able to visualize. Now think logically. How much flux might be going through this cube can be calculated by imagining another bigger cube over here. So let's just imagine a big cube over here, something like this, such that this charge Q becomes the center of that big cube. Yes, this charge should become the center of this particular big cube. Let's do that. Imagine it like this. Just visualize this. See, are you able to visualize this now? This is at the center of a big cube out there. See if you're able to visualize. It's at the center of a big cube. This is a big cube of 2 times the side length. So now that particular charge is at the center of it. And can you visualize there will be actually 1, 2, 3, 4, 5, 6, 7, 8 such cubes? Are you able to visualize there will be 8 number of such cubes over there? Yeah, think about it. There will be 8 number of such cubes out there. So this cube flux will be exactly 1/8 the flux of that particular big cube, 1/8 the particular flux of that big cube. And because the charge is at the center of that big cube, for a cube where a charge is at the center, the flux is simply Q by epsilon naught. And this answer comes simply via Gauss's law, because that charge is completely inside that big cube. So the total flux 100% should be Q by epsilon naught. So hence this answer will be 1 by 8 times Q by epsilon naught for the flux through that particular cube over here. Very interesting question, isn't it? It is 1/8 of it. It is 1/8 of it. So these kind of visualizations might be needed for certain questions where you might have to imagine another big cube or small cube or whatever, and then figure out, okay, for that big cube, that charge is at the center and the flux is going everywhere. and the total flux for the big cube is q by epsilon. So whatever is there, 1/8 is going here, because you can imagine 8 such cubes over here. So 8 such smaller cubes make that big cube, right? You might have played with Rubik's cube or whatever. So that gives you that idea. Everyone with me on this? Awesome. So I think this homework question you will be able to do after this. It's something like that. If you see the side lens, you will quickly understand which kind of question it is. Okay. So let's do some applications of Gauss's law. So that is the final part of this lecture. Okay. So let's do applications of Gauss law. Now, please remember, when we apply Gauss's law, cyclic integral, electric field dot that area vector is basically net charge inside by epsilon naught. Always choose a closed surface. So always choose a closed surface which is basically convenient. And when I say convenient, usually symmetrical. And in such a way that the electric field is either parallel or perpendicular. Electric field is parallel or perpendicular to the area at any place. This is preferable. This is what you prefer the field to be. Because if it is parallel, if the electric field is parallel to the area, then it will not pierce it. The flux will be 0. If it is perpendicular, then it will pierce through it and there will be 100% some flux. So you will try to do this kind of questions by choosing such surfaces which are symmetrical and field is parallel or perpendicular. That will make the calculations easy. Also keep in mind that you use Gauss law usually to find field due to certain geometries which otherwise are difficult via Coulomb's law. So that is when you use this. Okay, keep this in mind. All right. So let's see the application. Things will be very obvious after that. Let's try to find the field due to a point charge, which is Q. Okay, let's try to find the field due to a point charge. So first things first, choose a Gaussian surface. This is our Gaussian surface. And the Gaussian surface over here is basically a sphere. This point charge is placed here. I want to find the field here. I exactly chose a Gaussian surface. It's imaginary. Remember, there is no actual sphere over there. It's an imaginary sphere. And after that sphere is imagined, I will also think about how the field lines will look like. The field will go everywhere in all the possible directions like this. Everywhere the field exists. But, I'm considering one such small element over here. This element will have a small elemental area which is nothing but dA. The field over there is basically E. So if I start applying Gauss's law, let's see what it will look like. Cyclic integral, electric field dot my area vector will be net charge which is inside by epsilon naught. The total charge present inside this imaginary sphere is only one singular charge, which is Q. Electric field and area vector, no matter where you go, even if you go over here and you see the area vector, that area vector will be like this. If you draw a surface here, that area vector will be like this. If you draw and small area vector here, it will be like this. Everywhere that area vector happens to be parallel to the field, and that is what we wanted. Either it should be parallel or perpendicular, which will make our job easy. Because it is parallel, what will happen? This dot product will be simplified. It will be nothing but integration electric field area vector into cos of 0. Everywhere the angle between them is a 0 degree. So theta everywhere is 0 degree. Everywhere. So cos 0 is 1. Electric field is the same at the same distance. So this being a constant jumps outside that integration. I am just left with dA multiplied by 1, and this is q by epsilon naught. Why did this jump outside? Because it was a constant. Because it was a constant and cos 0 was 1. Okay. Next thing, electric field is there. What will be integration of dA? Just think about it. What will be integration of dA? And every area has to be covered. It will be area of the sphere, and area of the sphere is nothing but 4 pi r square. So that is q by epsilon naught. So when I integrate this area, it will be nothing but area of the sphere, the imaginary sphere which we have counted. Take that 4 pi on the other side. So you will see this can be written down beautifully as 1 by 4 pi epsilon naught. Q stays on the top. This r square stays here. This is exactly what we expected it to be. Kq by r square. If you remember Coulomb's law, electric field was K, Coulomb's constant divided by r square. Exactly what we wanted. So when you are wondering, sir, where does that 4 pi come from? It comes exactly from here. So this is the formula which we anyways wanted. Kq by r square. Is this absolutely clear, my dear students? Right? So this is how that 4 pi constant comes along with that permittivity in that Coulomb's force. All right. Okay. Thank you so much, Vijaya. Perfect. Awesome. Now that we are able to understand, okay, sir, we can find it for a point charge. Anyway, sir, this we knew, sir. There is nothing great about it. Do for something interesting. Fine. Let's do that. Let's take for a line charge. A line charge means, imagine a wire which is uniformly charged everywhere, and the parameter which will define how much charge is there on that wire is lambda. So lambda is called as the charge per unit length, and the unit of that is basically coulomb per meter. Coulomb per meter. Linear charge density. Linear charge density. How much charge is there per meter of that wire? Per meter of the wire, how much charge is there? Okay, that is linear charge density. Okay, now what happens? How will the field lines look like? First, let's imagine that. Because it's a very long charged wire, the field lines will spread out everywhere. And maybe some field line will go here, maybe some line will go here, maybe some line will go here, maybe some line will go here. Same thing I can say about here and here, like this, and maybe here also like this, and maybe here like this. That's how the field lines will go everywhere. So if you are if you now imagine rather a Gaussian surface which is a cylinder. So visualize this. This is basically your cylindrical Gaussian cylindrical Gaussian surface. If you are at some distance r from that wire, everywhere on that curved surface of the cylinder, the magnitude of the field will be the same. The magnitude of the field anywhere will be the same on that curved part, because you are at the same distance from it. So here, the field strength will be the same. The number of lines density is the same. So field strength will be same everywhere on that curved surface. So that is one thing. So this was already done. Okay. So I can say that this field is same on the curved surface. On the curved surface. Very, very obvious. Okay. So let me also choose an area vector over here. The area vector is going to be like this. And the best part is that the area vector is making 0 degrees with the electric field. So when I use my Gauss's law, which is electric field dot area vector, electric field dot area vector is net charge which is there inside by epsilon naught. Think about it carefully. This total flux will be the flux of the curved surface and the two flat surfaces. So the cyclic integral means the net cylinder. So I can say it is flux of the flat surfaces. There are two such, plus integration of electric field dot area vector only for the curved part. And this is inside charge. This is inside charge by epsilon naught. Notice how I have missed the cyclic integration or closed integration over here, because when I had one term, it meant the whole cylinder, but the whole cylinder comprises of three parts, two flat surfaces and a curved surface. So the two flat surfaces, I wrote it once, and curved surface, the entire curved surface, I have just mentioned it over here. But the flat surface will not have only any flux. Think about it. Why? Because the flux, the field is parallel to the surface. So there will be no flux. There will be no flux on the flat surface. On the flat surface. So this thing, quantity will be a big fat 0, guys. Yes, so this will be just 0 multiplied by 2, which is anyways 0. Plus integration on that curved part, electric field and the area vector everywhere make a 0 degree angle. Okay, fair enough. What is the charge which is present inside over here? Meaning, how much charge is just there in this much part? The logic for that is simple. If I want to measure how much charge is there inside the cylinder, okay, how much charge is there inside the cylinder? Use this principle. Lambda is whatever charge is there inside upon the length on which it is. The length is basically L, as you can see over there. So I'll just put L. Therefore, the net charge inside is lambda multiplied by L. L is basically the height of the cylinder. L is basically the imaginary height of the cylinder. Okay. So let me substitute that over here. So I'll just put it over here as lambda multiplied by L. This is 0, so forget it. This E being a constant will go outside. This is a constant, I just told you. So this is a constant, so it will just go outside. So I will be left with electric field into integration of dA will be lambda L by epsilon naught. Okay, fair enough. Let me go on to the next slide and work with this. Okay, so I just got E integration dA for that curved part is lambda L by epsilon naught. What is the area of the curved surface of a cylinder? It is the circumference multiplied by height. So circumference is 2 pi r multiplied by height, which is L. So that is equal to lambda L by epsilon naught. Needless to say, this L and L just got cancelled over here, which is a good thing. So therefore, electric field will be 1 by 2 pi epsilon naught, 1 by 2 pi epsilon naught. Lambda is there on the top, R is there below. If you want, you can write this as electric field is 1 by 4 pi epsilon naught 2 times lambda by r, which is the same as writing I multiplied by and divided by 2, k multiplied by 2 lambda divided by r. So many people prefer to remember it like this, k into 2 lambda divided by r. That is the electric field due to a long charged wire, infinitely charged long wire. Okay, everyone with me? Yeah, cool, awesome, awesome. All right. Electrostatics almost done. One more lecture we can just do maybe problem solving, but that is not going to be lecture. So we can do problem solving. That is basically on conductors we have to do. So we can say one more lecture, but we are going to start capacitors after that. Okay. So one last class and then capacitors. Okay. Yes. Rangampeta, definitely, man. You can crack J. You have time. And if you delay it further and if you ask me in July, I will still say yes, but the chances start becoming less. So start now. There are many kids who realize their potential and their seriousness now onwards. You can definitely get a good percentile in January attempt. Maybe not the best, some good percentile, and you can improve by April attempt. Maybe if you get a good percentile in J means January attempt itself, then you might start preparing for J advance, and you can just chumma give April attempt and see if it improves. Great. And you are anyways preparing for advanced, so 100% it will improve, and you have simultaneously started your J advanced journey. So you can definitely get into IIT starting from today. Okay, just make sure you cover your syllabus by October, November, maximum November, and make time for revision from November and November mid onwards. All right. Thank you so much, guys. All right. So moving on to the next kind of question, which is the field due to a uniform charge sheet. Yes, if you have a long sheet, how will the field due to it look like? First of all, the parameter to define the quantity of the charge present on the sheet is called as the area charge density. Area charge density, the symbol for that is sigma, which is nothing but how much charge is there per unit area, and the unit for that, because it is charge, so it will be coulomb, and area is meter square, so coulomb per meter square. Now in order to figure out how much is the field, one thing is very obvious, that the field will look something like this. It will be uniform. It's a large sheet, guys. The field will be everywhere like this on both the sides. It will go here also and here also. The interesting thing in this problem is that this electric field is uniform electric field. Everywhere it is going to be the same. When you saw this problem, it dependent on the distance. Yes, it is dependent on the distance. Even this one over here, it is dependent on R. As you can see, when you go away, the field lines go far away. So it is non-uniform field. But in this scenario, when the sheet is present, the spacing is the same. So the strength of the electric field is the same no matter where you go. No matter where you go. So this is very important to solve the problem. You start off by choosing a Gaussian surface like a cylinder over here, which is piercing through the sheet. So this is our cylindrical Gaussian surface. And because our electric field will come here like this and also over here like this, but it will not pierce through the curved surface. It will not pierce through the curved surface. Visualize this. None of the curved surface will be affected by it because it will be parallel. So the good thing is the flux through the curved surface will be zero. So the flux through the curved surface will be zero. There is only flux through this circular face and this circular face. That's it. Only these two faces have flux. Okay. So start off with the Gauss's principle, cyclic integral, electric field dot area vector is the net charge which is inside by epsilon naught. Okay. Net charge which is there inside by epsilon naught. I will not touch it now. Over here, the total flux through the cylinder is the sum of two faces which are flat and the curved surface. So I'll put 2 times the flux through the flat surface plus the flux through the curved surface. Now I know one thing, this flux through the curved surface is ready-made zero. Even if I put integration symbol, doesn't matter. It is zero anyways because the field lines are parallel. It is not piercing through it. It is parallel. The field lines are parallel. So when the field lines are parallel, guys, as you can see over here, and the field lines are parallel, they will not cause only any flux. They will not cause any kind of flux. Okay, so don't have to worry about it. All right. What about the flux through the flat surface? Okay, as you can see, it will be this area. I can call this shaded area over here, which is in pink, as A. The field over here, which I want to figure out, as E. So it will be just electric field multiplied by that area. That's it. And the angle between them, as you can see, theta is 0 degrees. So EA cos 0 degrees plus 0 is inside charge by epsilon naught. Is inside charge by epsilon naught. Now, how much is the charge which is present inside? Observe carefully. This is that charge. This is the charge which the cylinder pierces through that sheet. This is the charge which is inside. And coincidentally, it will so happen that whatever is the area of the flat base will also be the area of this intersection. It will also be the area of this intersection, right? Whether you take this, this, or this, all three are the same. So all of them have the same area. So going by this definition of charge density, charge inside is whatever there upon the area. So therefore, the total charge which is inside is sigma multiplied by A. So this is the total charge which is present here. That is what we have to consider. Okay, so sigma into A is the answer over here. So sigma into A by epsilon naught. As you can see, over here, this area and this area just got cancelled. So I'm left with 2 times of E, cos 0 is 1, is sigma by epsilon. So electric field is just sigma by epsilon. That's it. That is the answer. It is just simply sigma by epsilon naught. Sigma by epsilon naught. Nothing more, nothing less. Clear? Very important. And as you can see, it is independent of the distance. So it is nothing but independent of the distance. Independent of the distance. So it is uniform as predicted. It is uniform as predicted. The strength will not become less or more. It's the same. Why can't we use thickness of the area of the cylinder? Rama, it has to be a closed surface. Yeah. So when you take a closed surface, right, it should be like this. Number one. Number two, you should always choose some charge inside, or else we cannot use Gauss's law. If charge inside is 0, RHS will become 0. What's the point of using Gauss's law? Okay. So that's the reason for it. Yeah. Right. So that number 2 is very important, guys. This is the field due to a large sheet. Field due to a large sheet. Now let's go the field due to a shell and a sphere. What's the difference? See, when I say a shell, it means literally a shell. The charges are only there. The charges on it are only there over here on that shell, maybe like this. Okay. And when I say this is basically a shell, this is uniformly charged sphere. Uniformly charged sphere. Yeah, uniformly charged sphere. In this case, the charges are not only there on the surface, but they are also there even inside. Are also there even inside. Okay, they are all there inside, outside, everywhere. It's uniformly charged. It's like solid sphere where the mass is there inside versus a hollow sphere or a shell where the charges are only there on the surface. So here charges are only on the surface. Charges are only on the surface. Here the charges are distributed in and on the particular sphere, inside also and on the surface also. Okay, that's the difference. Now what happens is, when you consider these geometries, the outside part answer will come out to be the same for the electric field. Whatever field you try to calculate, right, the outside part will come out to be the same. It's only the inside part which is different for both these geometries. Okay, it's only the inside part which is different for both these geometries. So outside it is the same, nothing different. I'll tell you why. Say for example, you take a shell or a sphere, you take a shell or a sphere. This was not needed. You take a shell or whether you take a sphere. Okay. If you choose this Gaussian surface, if you choose this particular Gaussian surface, and let's say I'm trying to find the field at this particular distance of r, of small r, this small r is more than or equal to the radius of the shell or the sphere itself, is more than or equal to the radius of the shell or the sphere itself. Okay, so this is our shell or the sphere, whatever you want to call it. Remember, the charges are there here, or maybe even inside, doesn't matter. Or maybe they are even there inside, doesn't matter. Okay, even if they are inside, okay, maybe they are here, something like this. Okay. Now, when you apply Gauss's law, what happens is cyclic integral E dot dA is net charge inside by epsilon naught. The total charge on the shell or the sphere, let's say it is Q. Let's say it is Q, and this is epsilon naught. Now see, like I said, the electric field lines will look something like this, which I have shown over here. So if you are at some distance r from it, the electric field at this point will be here, same over here, same over here, same over here. Uniform symmetry should be there. So everywhere it will be symmetrically distributed. So the electric field lines will look like this. So this is our electric field line. This is our electric field. Similarly, at each point, the area vector will be like this. The area vector will be like this, parallel to the field. The angle made with the field will be 0 degree. The angle made of the area vector with the field will be 0 degree. So when I use our Gauss's law, it will be nothing but E into dA into cos of 0. Cos 0 is 1. I will be left with only integral dA because electric field will shift outside. Why has it shifted outside? Because it was a constant everywhere. Okay, fair enough. This will be Q by epsilon naught. Integration of that area, that means this area, the Gaussian surface, it will be 4 pi small r square. Be careful, not the area of the sphere. It will be 4 pi small r square. Yes, a lot of students make a mistake there. So that will be Q by epsilon naught. So this electric field comes out to be 1 by 4 pi epsilon naught Q by r square, which is the same as saying it is K Q by r square. This clearly tells me that this electric field is similar to that of a point charge, is similar to that of a point charge at the center, point charge which is present at the center, kq by r square. Very similar, no difference in that. So whether it is a shell, sphere, uniformly distributed, not distributed, outside part is the same. So this was all outside ways. Everything that we calculated was outside, whether it is a shell or whether it is a sphere. But when you go inside, things will change. For example, if you are inside a shell, remember the charges are only there over here. The charges are only there over here, nowhere else. So if somebody decides to make this as their Gaussian surface, this is your small r, This is the radius of the shell, capital R. So our capital R is more than our small r, or small r is less than capital R. Then the interesting part of this problem is that when you use Gauss's law, electric field dot area vector is net charge inside by epsilon naught. There is no charge inside the shell because all the charges are there on the periphery. So there is no charge on this Gaussian surface at all. Yes, there is no charge at all. So this will be 0 by epsilon naught, which is a 0. What does this tell you? If integration of electric field dot area vector is 0, it just means that the electric field is 0 everywhere inside. So no matter where you go, everywhere the field is 0. So field is 0, this is the net field, is 0 inside, anywhere. Anywhere you go inside, it is 0. Here, it doesn't matter, it is 0. All the fields will cancel out each other. That is the interesting part for a shell. But the moment you take a sphere which is uniformly charged, things will begin to change because there will be some charges which are present inside our Gaussian surface, whereas some charges which are not, like this one's over here, like these charges over here, these charges are outside that Gaussian surface. They are outside that particular Gaussian surface, as you can see. So when you apply Gauss's law, and you say it is net charge inside by epsilon naught, well, over here, this electric field here at this distance r, this electric field over here at this particular distance r, which you are able to see, again this small r is less than your r, which is this r is less than this r. Then you will see again at every place that area vector which you take, is parallel to our electric field. Area vector which you take is parallel to our electric field everywhere. So this will again become E dA cos 0. Cos 0 is 1. Electric field will come outside. So it will be nothing but, just happen. My board has hanged. Okay. Hold on just 1 second. Let the board cool down. For some reason the board has hanged. I just hope the data stays as it is. It doesn't go away. Okay. Yeah. It is not going. So it will be E integral of dA, cos 0 was anyways 1, is equal to integration of dA. That means integration of this particular area of that Gaussian surface, which will be nothing but 4 pi small r square, Next step, we can take it on the other side so that we get the value of the electric field, which is 1 by 4 pi r square and whatever was there over here. Now be careful, whatever is the charge inside will be only that green part, and we can use this logic. My God, what is this? We can use this logic that the density of the charge is the same. It is uniform charge distribution. The charges are distributed in and on uniformly. So we can use the concept that the charges are distributed uniformly. So if I say that the charge per unit volume is going to be the same, if I just say the charge per unit volume is going to be the same, in this part, the charge is whatever charge is inside by this volume, which is 4 by 3 pi r cube. Whereas for the entire sphere, the total charge would have been capital Q and the total volume will be 4 by 3 pi capital R cube. That's it. The charge per unit volume would have been same. 4 by 3 pi cancels out. So that way I will get that the charge which is there inside is capital Q small r cube by capital R cube. This is a very interesting thing, that I am only dependent on the charges inside, not on the charges outside by Gauss's law. The charge inside is inside of the sphere of radius small r, so that volume. The total charge Q is on the total volume whose radius is capital R. So cancelling 4 by 3 pi, I get this. So substitute that over here. Substitute that over here. So it will be nothing but total charge small r cube by capital R cube, and this whole thing divided by epsilon naught. So if you put that over here, q small r cube divided by capital R cube 1 by epsilon naught, r cube and r square will cancel. So I will be left with 1 by 4 pi, epsilon naught is there, Q is there, a single R is there, and capital R cube is there. So therefore, the electric field will become, this is a Coulomb constant into Q into small r, whole thing divided by capital R cube. So this becomes your formula for the electric field, which is inside a uniformly charged sphere. It is linearly proportional to R. Linearly proportional to R. Okay. So if we were to draw the graph of how the field looks like, if we were to draw the graph of how the electric field looks like with distance, one is for a shell, this is for a solid sphere, outside everything is same, but when you are inside, how things change. For a shell, I just told you, when you consider a shell, electric field is zero everywhere. For a shell, inside everywhere the field is going to be zero. So this graph will be just flat. But for a solid sphere, it is proportional to R. For a solid sphere, it is just proportional to R. So it will just go like this. So you will see that the electric field is proportional to R. Here, the electric field will be zero when you are inside. But the moment you reach the surface, which is radius r, then outside it is just inversely proportional to r square. So it will go like this. Electric field is inversely proportional to r square, as you can see over here. It just behaves like a point charge. It is inversely proportional to r square when you are outside the shell or the sphere. This is how the graphs look like. This is absolutely clear, my dear students. Perfect. Amazing. Similarly, you can also draw the graph for a cylindrical shell, for an infinitely long wire, How will the field look like with distance? As you can see over here, it is inversely proportional to R. So if it is inversely proportional to R, it will look basically like this. The electric field will be inversely proportional to R for a long wire. If you ask me what is this curve, it is a rectangular hyperbola. Whenever you have inverse relation with the power 1, it is a rectangular hyperbola. Don't say that, sir, even this graph, sir, is a rectangular hyperbola. No, it is just a random curve. It's like a hyperbola, but it is not a hyperbola. Okay. So it is 1 by r square. 1 by r square graphs are not hyperbolas. Keep that in mind. Cool. So these are your applications of Gauss's law. But there is one more critical application which I would like to talk about. This is a more of J advanced concept. And let me remind you that we had spoken about something like solid angles in units and dimensions. So just imagine something like, a sphere. Okay. And okay, so just imagine this sphere over here, and a 2D angle is a normal angle, a three-dimensional angle that's called as a solid angle. What is this concept of solid angle and where is it used in Gauss's law? Let me just come to that. So just imagine if I tell you, just like we had length of the arc is radius multiplied by the angle in radian. What if I told you the area on the surface of a sphere which you are considering is radius square multiplied by the solid angle being considered? It's very similar looking, same, but different. So what do I mean by that? So say for example, you are considering a patch, over here. Okay. This is on that surface of that sphere. So just visualize this from the center, okay, like this. Okay. There is something which is subtended. At the center, which is now in 3 dimension, which we call as the solid angle. So this is that area on the surface of the sphere. This small thing which is subtended, it is in 3 dimension. We call it as a solid angle. You can call it psi, phi, whatever you want to call it. Okay, you can use different symbols. Theta, usually we use it for 2D angles. This is your 3-dimensional angle. So this is your 3D angle, which is now called as the solid angle. Visualize that patch which is there over there, it will subtend in 3 dimension, not in 2D, not between two lines. Here I can't show 3D. Imagine there will be many such lines over there, many such things over there. You'll have to literally visualize that 3-dimensional thing over here. So that is that solid angle. So over here, I can just say that this particular area will be whatever is that radius, whatever is this particular radius square multiplied by psi. Now, if you take the complete sphere, observe this, for entire sphere, the area is basically 4 pi r square. R is R only, psi is psi. R square cancels. What will you get? Psi is basically 4 pi steradian. This is very important. If imagine that patch spread on that entire planet, that entire sphere, the entire angle, like we say, if you rotate once, you complete 360 degrees. So, the entire 2D angle, if you come back, if you cover everything 2-dimensional, you say you have covered 360 degrees. Same in 3 dimension, if you cover everywhere, you shoot everywhere, you see everything. It's like a 3D viewing camera. You see everything. You have covered a solid angle. Of 4 pi steradian. How much solid angle? 4 pi steradian. Is that clear? So can you now guess, if it was a hemisphere, how much will be the solid angle? Can you guess how much will be the solid angle for How much will be the solid angle for a hemisphere? Solid angle for a hemisphere, for a hemisphere, it will be obviously 2 pi steradian. 2 pi steradian. Is that absolutely clear? Solid angle for a hemisphere will be 2 pi steradian. If you break that hemisphere also into half, see, this is like your hemisphere. This is like your hemisphere. If you break that also into half, this part, half of that hemisphere, half of this hemisphere will be pi steradian. Just visualize that, okay? So that is how you can keep on breaking it into parts. Yes. So now comes the real question. If you have, if you have a flat circular base, or if you have just a circle like this, okay, and let us just say from that circle you are over here, and this is also imaginary. Actually, this is an imaginary cone. It's an imaginary cone. Then how much solid angle is subtended over here? How much solid angle is subtended over here? This is for a cone. So if the actual semicone angle theta is called as a semicone angle, semicone angle, obviously this is going to be in a radian. This is going to be in a radian. Okay, this is going to be in radian. This is going to be in radian. Psi is the solid angle subtended by this particular part over here. Psi is the solid angle subtended by this part over here. That particular answer, okay, if you want to find it, that particular answer, if you want to find it, what is it going to be? Yeah. Any guesses, guys? Any guesses? It will come in cos. It will come in cos. And let me tell you, it will be something 1 minus cos theta over here. And you will have psi over here. And there is something which is going to be there over here. What number could it be? Okay, just think. If I make theta as 90 degrees, then theta is 90 degrees, then it will almost become like an infinitely large sheet over here on this side. So, you know, it will be one side of the hemisphere, you can say, one particular side of the hemisphere. So the answer should be 2 pi radian if theta is 90 degree. So if theta is 90, if theta is 90, cos 90 will be how much? 0. 1 minus 0 is 1. So the answer should be 2 pi. So over here, you should put 2 pi. That's it. That is the answer. So this is the solid angle subtended by the base of the cone. This is the circular base of a cone, imaginary cone. How much is the solid angle being subtended? So psi over here is the solid angle being subtended. Why is this important? You might be asking. Why is this important? You might be asking. The answer is simple. If you have a point charge, then the electric field will go in all the 3 dimensions, inside, outside, towards you, inside, outside, towards you, away from you, everywhere. In fact, it will go in a, imaginary sphere like structure. Imaginary sphere like structure. Just visualize this. Just visualize this for a moment. It is going everywhere in a spherical direction. Everywhere. Just imagine a sphere. From that sphere, it is coming out from all the sides possible. So if you take a sphere whose solid angle is 4 pi steradian, the flux through it is q by epsilon naught. The flux through it is Q by epsilon naught. So imagine, just imagine, if I know that I have some surface over here and it is and it is subtending some kind of solid angle, let's say psi, how much flux will pass through this? How much flux will pass through this? If that is the question, just think about it. It's like a unitary method. It is like an unitary method. So if I want to find the flux, if I want to find the flux for a solid angle, for a solid angle of psi, whose value I just calculated to be 2 pi 1 minus cos theta, which is 2 pi into 1 minus cos of theta. What am I going to do? What am I going to do? Just unitary method, guys. So this much flux for 4 pi steradian. How much flux for this many steradians? So it will be nothing but Q by epsilon naught is the flux per 4 pi steradians into 2 pi multiplied by 1 minus cos theta will give me the flux through that particular base. Pi 2 cancels. So therefore, that flux which I get, the flux which I get will be Q divided by 2, only the number 2 remains, with epsilon naught, and I will have 1 minus cos of theta. Now this formula is very important, obviously, for calculation purposes. This formula, you remember, obviously this is also important, you can say, but the final derivation result is very important